Chapter 13.5. Now in this section we are going to consider surface integrals. So if you recall chapter 13.2, in that section we consider line integrals, and specifically we consider two types of line integrals. We consider the line integral over a scalar field or a scalar function, and then we consider the line integral over a line integral of a vector field. Now when I consider a line integral, here I wrote d little s, and here I wrote d little s with an arrow because this is a vector quantity. Now in this section, in 13.5, we are going to define an integral over a surface. So a surface integral is a definite integral. Taken over a surface. So this one is very similar to 13.2. Now instead of a line, now we have a surface. Now given a surface, one may integrate over its scalar functions and vector fields. So basically the integrand can be a scalar function or a vector field. So first we are going to consider the surface integral of a scalar function. Let's do that. Surface integral of scalar function. Okay, now surface integral of scalar functions. Let me draw a picture. So we have this x, y, and z axis. X, y, and z axis. Now here we have a surface S. So we have a surface S like this, big S. Now let's say the equation of this surface is z equals to f of x comma y. Okay. Now if you project this surface onto the xy plane, you will get the domain of this function. Maybe let's say this is your domain D on the xy plane. That's your domain D on the xy plane. It's your domain of this surface S on the xy plane. Okay, now on this surface we have a function with three variables. So on this surface we have a function, let's say f of x comma y comma z on S. And as you know, we are unable to draw this function in three-dimensional space because this is in R4, but on this surface, on every point on this surface S, we have a function value. I will draw it like this, but this is in R4. So every point on this surface we have a function value. This is the surface, this is the function value, this is the surface, that's the function value, and so on. Okay. Now let's define the surface integral. So let S be a surface with the equation C equals to f of x comma y, and D be its projection on the xy plane. Okay. So again, remember this. So we have a surface S. Domain of this surface S is D. Now let g of x comma y comma, no, so not g, sorry, it should be f. Let f is a function with 3 variables. Let f be a function with 3 variables defined on S. Then the surface integral of f over the surface S the surface S is given by the following equation. Your equation is this. This is a surface integral, so we have a double integral. Now we have this f defined over the surface S. Now if you recall chapter 12.4, this ds represents a surface area element. The surface area element. Okay, now to evaluate a surface integral of a scalar function, what we do is first we evaluate this function f on the surface. So on the surface, your c coordinate is given by the equation of the surface, which is this. So we have f of x comma y comma. Now instead of c, we write little f of x comma y. Okay. I think we should change the letter. So we have 2 little f, so let's change this function to be g. So then we have to change this to be g. This must be g as well. Otherwise I have the same letter for 2 different things. Again, for the surface S, I use the equation C equals to f of x comma y. Now on this surface we have a function g of x comma y comma c. Okay. So what we did was we evaluate this function g on the surface. Now on the surface x coordinate is given by x, y coordinate is y. However, your c coordinate is given by the equation of the surface, which is f of x comma y. Now instead of ds we should write the area element. Now in chapter 12.4 we define this ds to be square root of 1 plus f sub x squared plus f sub y squared dA, where dA is an area element on the domain D. Area element on the domain D. So this is the way we define the surface integral of a scalar function.